We present a novel, highly parallelizable method to extract planes for organized point clouds. My name is Hannes Mölz. I'm a student research assistant at the Intelligent Sensor Actuator Systems Lab at the Karlsruhe Institute of Technology. This is a joint work done together with my colleagues Kai-Lai Lee and Uwe Hannebeck. Real-time dense lamp systems have made great progress in recent years, but often require gigabytes of fast memory to function. This is due to the underlying scene representations. In order to use alternative scene representations, a fast segmentation step is required. Especially indoors, finding planes can be a good alternative since human-made environments are predominantly made up of planar surfaces. Detecting planes in an image sequence can also be used for tracking, as large planes are robust landmarks and compensate well against noise. Furthermore, planes have a very small memory footprint. All currently existing plane extraction approaches can be categorized into three classes. Ransec approaches have to test large numbers of potential inlier-outlier splits of the input point clouds, which is very time-consuming and computationally expensive. Because the borders between planes is unknown, a hierarchical trial-and-error process is commonly used to first find these and then refine them. Even GPU implementations can only achieve less than 10 Hz on the full input resolution. Using the Hough transformation introduces a loss of precision because it works by voting in a discretized voting space. This voting space also requires large amounts of memory, which makes it no longer eligible to fit in fast GPU caches. Region-growing approaches utilize the grid nature of organized point clouds. By starting at an arbitrary seed point, neighboring points are recursively considered to be clustered to the same plane. While being faster than the Ransec and Hough transformation counterparts, region-growing approaches are difficult to parallelize, as each region-growing step results in a new explicit representation of the cluster or plane. We introduce a novel region-growing plane extraction method, which is based on an implicit plane representation and is therefore inherently parallelizable and real-time capable. Our method is based on clustering normals on the S2 sphere by employing the convex hull. A convex hull of a set of points is the smallest polygon that contains all points. This concept can be extended to points on a sphere. Instead of the Euler distance, we employ the arc length. To decide if two normals are part of the same plane, we define a plane extraction condition. In our definition, normals are part of the same plane if a plane normal mu exists, so that the individual angles between the plane normal and the point normals is less than a predetermined theta. If at least one mu exists, then the given point normals lie on the same plane. To better understand this, the algorithm will first be explained in the two-dimensional case. On the left side is a two-dimensional organized point cloud. Normals like the blue one can be calculated and displayed in the space of normals on the right side. A plane extraction algorithm based on normal averaging would fail this particular point cloud, as in each step the total average normal would be dragged along the curvature during region growing, thereby falsely classifying the entire surface as a single plane. On the contrary, our algorithm approximates a curved surface like this with multiple planes by maximizing the cardinality of the contained normals while also satisfying the aforementioned condition. The condition can be depicted by a red arc segment with a length of 2 theta. Because we currently only observe the blue normal, many mu exist which satisfy the condition. The condition should hold when considering the next normal, here green. Note how mu has less freedom. The next normal, purple, is added and fully constrains mu. The green normal is not contributing to constraining mu, but only the two most outer normals. The next neighboring normal, here in gray, lies not in the plane of the first three normals because no mu can be found which would cover all four normals. The gray normal would therefore start a new plane. Note that when checking if a mu exists, only the two most outer normals are required. In fact, mu never needs to be explicitly calculated because its existence can be quickly inferred from the two outer normals. The same applies for the three-dimensional case on S2, in which the equivalent of the two most outer normals is the spherical convex hull. Now in 3D, a single normal blue and an arbitrary mu containing the plane normal. Note that the circle has a radius of theta. We introduced the concept of the cluster permissible region, which is an approximation of the union of all valid mu's. The CPR never gets explicitly calculated, but can be directly inferred from the convex hull. A second normal, violet, is covered by the CPR of the blue normal. Because the violet normal is within the CPR, a plane normal mu containing both plane normals can be assumed to exist. There are many plane normals satisfying the plane existence condition, while containing both normals. An arbitrary one is shown here. The new CPR is created by intersecting individual CPRs of the normals. A third normal, green, lies within the CPR of the blue and violet normals. Accordingly, a potential plane normal mu exists, which contains all three normals. Note that mu is now more constrained than previously. The new CPR of all three normals is created via intersection. Now a convex hull is formed by the three normals. All further incoming normals can be quickly processed by following the algorithm on the right. A new normal, cyan, was added and lies within the convex hull. Therefore, it is part of the current plane but does not update the convex hull nor the CPR. A new normal, again cyan, lies outside of the convex hull and outside of the CPR. Therefore, no plane normal can be found for all four normals. It is thus not added to the current plane. A new normal, cyan, lies outside of the convex hull but inside the CPR. Therefore, the convex hull is updated and shrinks the CPR via intersection. Note that the valid plane normal set, meaning the red circle, is constrained even more. This is a live demo of the presented algorithm running on a single plane. On the right side is a normal map of a single frame from the TOOM RGBD dataset. The black rectangle are already processed points. On the left side is a depiction on the S2 sphere. The orange polygon is the CPR. The white core is the current convex hull. Blue normals contributed to it at some point. Green normals were only clustered without changing the convex hull. On average, more than 99% of the normals fall inside the convex hull and therefore are very quick to process. Based on the proposed algorithm, we introduce a lightweight plane extraction pipeline. To find suitable seed points, we search for fixed-size patches with a low variance. This seed point list will then be processed iteratively by choosing seed points which have strongly different normals to avoid flooding the same plane twice. After each subset was processed, indirectly processed seed points are removed and new ones are selected for the next iteration. This is repeated until the entire seed point list is empty. The proposed algorithm was implemented in C++ and CUDA. Even though it is computationally intensive, it is inherently parallelizable and can make full use of graphics cards. More specifically, its parallelizability can be interpreted in three execution levels. 1. At the pixel level, validating the CPR and the convex hull for a single pixel normal can be easily parallelized. 2. At the plane level, parallel validation of normals with respect to the same CPR and convex hull is done by different CUDA warps. 3. At the seed cluster level, multiple planes can be processed from different seeds in parallel using different CUDA thread blocks. This high parallelization results in an average processing time of 70.7 milliseconds, which to the best of the author's knowledge is the fastest and first real-time capable plane extraction algorithm for the full input resolution. The presented time was captured on a low-cost laptop GPU which is comparable to the popular NVIDIA Jetson TX2. The precision of the proposed algorithm was evaluated on two public datasets. It achieves state-of-the-art accuracy. It should be noted that the high angular deviation alpha of the proposed algorithm could be further refined by calculating its plane normal after the finished segmentation using PCA or similar. The second fastest algorithm after the proposed is PEAC, which takes on average 120 milliseconds per frame. This is almost 7 times slower than the proposed. Besides finding planes, the presented algorithm is also capable of approximating curved surfaces with many smaller planes, which can be here seen on the globe. However, this could also be suppressed by calculating the variance for each plane and removing those with a too high variance. Our method is also capable of differentiating between parallel planes. The high speed is the result of the implicit parameterization of the planes, which infers no execution dependencies and therefore allows for independent data processing. The presented novel region drawing algorithm is to the best of the author's knowledge the first plane extraction method capable of full resolution processing in real time for the current generation of depth cameras. It only requires a low-end GPU which for most dense SLAM applications is already present. In the future we want to further improve its precision, speed and robustness and also develop a new kind of dense SLAM system based entirely on plane tracking and a plane scene representation. Thank you for your attention.